So, good afternoon, everybody, and welcome to July edition of the Numerical Analysis Research Cluster Seminar Series. And today we are going to be having a very good friend of mine, my collaborator, and my very good friend from the US. His name is Professor Luan, and he will be teaching us on a topic: advanced exponential and multirate integrators for. Sorry, Luan, can you wait? Let me share my screen first.
Okay.
Okay. So you'll be talking to us on advanced exponential and multirate integrators for multiple time scales problem. I'll call on Miss Festa to read the bio sketch of Professor Luan. Festa, over to you.
Yeah, good afternoon, everyone. Can you hear me?
Yeah, we can hear you.
Okay. Dr. Luan is an associate professor in the Department of Mathematics and Statistics at Texas Tech. He received his Ph.D. in applied mathematics from the University of Innsbruck in 2014. Prior to joining Texas Tech, he held faculty positions at Mississippi State University and visiting appointments at University of California, Merced and Southern Methodist University. His research lies in numerical analysis and scientific computing, with a focus on the development of high-order time integration methods for stiff and highly oscillatory systems, such as exponential integrators, multirate method, and two-derivative scheme, with application in numerical weather prediction, visual computing, and computational biology. He has been the principal investigator of several grants awards by NSF. He serves as an associate editor for advances in applied mathematics and mechanics, and has actively contributed to the organization of scientific conferences, workshops, and summer schools. Thank you.
Okay, so Professor Luan, you can share your screen.
Okay, thank you. So this one. Can you see my screen now?
Yes.
Okay. Yeah. Can I start now? Or?
Yeah, you can start. Yeah.
Okay. Thank you so much for the invitation and the introduction. So yeah, so as Juliet mentioned, I will talk about basically the kind of recent developments of exponential integrators, and I mentioned also a little bit about the multirate time integrators. All of this for showing basically we call it a steep problem, or you can understand like a multiple time scales problems where the problem have a different time scale. So this is supported by NSF. So the first part I just mentioned briefly about the motivation, and then the class of problems that we're interested in, basically the steep or multiple time scale problems. And then in the second part, we'll talk about exponential methods, basically, and also a little bit about the multirate time integrators. And then I mentioned about the three applications that we can use this kind of method in visual computing, in weather predictions, and in computational biology, where this is actually one of the we work with Julius here. All right, let's start with the first part. So our research mainly driven by looking at the so-called multiphysics problems. And you can see like in in science engineering, many problems that involve multiple physical processes where different complex different components have different time scale, then they interact in a complicated ways, and so So for instance, when you look at this picture here from NOAA, where you have the modeling of the Earth system there, we have the quite different physical processes in the motor. You could have, I mean, in the atmosphere, in the ocean, or in the land, different processes. I mean, advection, diffusion, or anything like chemistries, reaction, and so on, and they interact each others, and they have quite different time scale. If you look at the advection, it's kind of slow, but if you look at the gravity waves, it's really fast, and so this is showing the quite different time scale, big gap in the system, and then we can actually model by this system by a system of PDEs, and usually derived from physics. Oh, sorry, fluid motion or chemistry, and of course, yeah, I mean, simulate many things like a wind speed, velocity, uh, humidity, so on. And so the major challenging in solving this system numerically or in real, it is a real-time simulation. Because of that difficulty, so basically traditional method is have to use very, very small, extremely tiny time step. And so so that very make the whole simulation very either slow or have to take even sometimes due to stability is not even can run. So so therefore our goal in this work is to develop fast and accurate time integration method for solving such multiphysics problems. Okay. So if you look at the some examples, specific example that I mentioned already, but if you look at some model in weather prediction, numerical weather predictions, and the simulated model that you can see, it's for instance a shallow water equation on sphere that describe the viscous flow on a very thin fluid layer on sphere. So you have u is the velocity, yeah, so the solution u velocity, and h is the thickness or the height, and so they can model using this kind of PDEs, and this is a very standard model. I think the first thing that people want to develop a new numerical method for weather prediction, they have to start with this model first. And then a little bit more complicated model is the Euler equation. So then you have now basically more components, density, pressure, and you along with also I mean other components like a temperature and so this model actually introduce consider also the vertical dimensions. Therefore, it's introduces steepness like gravity waves, and so now when you look at the system of PD model like that, you can actually write in the compact form by introducing the vector rotation. Yeah, depending on how many equations in the system, how many components you actually can put in the compact form, like a dx over dt equal to f of x, where f of x is a forcing term, including all of the right-hand side of the motor, and the x is a variable including the components that unknown variables, like you have m equation in the system that have three m unknowns. So so then I think to my understanding is that we have two main approaches to in terms of the time integration for solving this system. The first one is the so-called Lagrange-based time integration. The idea is to, so this is still the compact form of the PD, okay? And so we discretize both in space and time together, so simultaneously. So discretize in x in t. And for instance, if you look at this one, it's just a simple way to think about that. It's just like you approximate the left-hand side, the derivative, time derivative of x, like that way, where delta t time step. But you also discretize x as well. So then the right-hand side, you can think about like you do fundamental theorem calculus. You do this integral where you can integrate both sides, and so you see that. And with this approach, there's a very famous method, the so-called semi-implicit semi-Lagrange method. That's look like this scheme that can use to to show this system. And then the second approach is that's the so-called Eulerian based time integration. Is that we have two things like a space and time we discretize independently. So if you discretize, usually, for instance, you discretize in space first, and you lead to a large system, initial value problem, ODE in time. This is a large system. And just a brief review is that the prominent scheme, the very famous scheme is the so-called the IMAX implicit explicit scheme, or the horizontal explicit vertical implicit heavy scheme. That's for this approach. So I'm mainly beyond the second approach, where we consider this, we discretize in space first, and then we get this large system in time. So here, for instance, our PD model look like this. So you have time-dependent PDEs. And so in this case, if you look at just like this example, we have, let's say, the unknown variable, the capital U, depending on the spatial variable x and time variable t. So I write in a very general form. It could be any dimension d. And so you have the strongly elliptic differential operator on the left-hand side, could be Laplace, or you could have Laplace plus some radian operator, so on. Then you have some non-unity term. So together with the boundary conditions. Now, the first step you do is to do the space discretization. Just think about like this heat equation, like this simple on the right hand side that I put a very simple example, like in 1D. So this is a Laplace, and this is a non-unity U squared plus some L at T. So you discretize in space, for instance, using finite different methods, or you can use anything like a finite element or spectrum method, finite volume methods, and so on. All of this lead to a large system of ODE. We could have the form either full nonlinear or semi-linear form. So you see that's semi-linear form. I mean that's the right-hand side can be split to linear path and non-linear path. Like so the script A operator becomes a metric A. So then the big nonlinearity G script tree becomes G of TU, or you could have a full nonlinear system where you cannot really see, you can split to linear or nonlinear path. So now look at this simple heat equation here. You see that we did just a finite different methods using the standard second order standard Pori, and so you can see that the little u here is approximate to the solution capital U at the grid side xi and then time t. So now we fix xi. I think this is called so-called method of lies. You heard about that? So you actually looking for the numerical solution on each vertical x equal to xi, where you fix x already, then you have this thing just depending on time. Now you have the system in little u prime equal to this red term, and then the blue term is the non-linearities. And so you actually so just write out as a metric time vector here, where the metric u a like this, and this is a very standard metric. You have seen many, in anything like numerical ODE, numerical analysis course, a triangular metric structure where we can even understand about the eigenvalues of this metric. Okay, so then, as I mentioned, time integration approaches could be anything like a Runge-Kutta methods, Rosenbach, IMAX method scheme. So yes. Oh, sorry. Kate, Kate. I'm just remind my kids to just make it now. Sorry. So I mean, then the main challenging here, for instance, you look at just the heat equation like this, you see the eigenvalues have this form where you have cosine -1. That gives you something. Just think about the real number. Then it's in a real space, it's negative quantity, but it's divided by delta x squared, which means that if we were in the space of discretization, delta x is the mass size. If delta x is small, then of course delta x squared, and then take the inverse of that, even much become larger, and you have a large negative eigenvalues, which means that the norm of this A is really large. And then for any classical method, you would have I would mention about the next slide, time step restriction about that, but that make the whole thing with the classical method it's challenging to show, and we call this is like a steepness, which means that the Jacobian, the full system had processed eigenvalue with a large negative real part of eigenvalues. So in more specific example is that in my research I have considered, for instance, advection diffusion reaction. So you have the quite different time scale in the system where epsilon is the diffusion coefficient quite small, but you have the gamma is the reaction diffusion. Reaction coefficient is quite big, so it's like 100, and then compared to a 1 over 100. So different time scales, and alpha just -10 for the advection path, and so on for the Allen-Kane equation. You see here with the 1 over epsilon square in the non-unit term, where epsilon is very small, so you could have a very big coefficient or large Lipschitz constant of the non-unity here. And other example, non-unit ringers, Rickenback system, and so on. In the pattern formation in turning bifurcation by its own kind of this kind of system can be considered as fit in this kind of model. So and then in the context of related context is that when you look at the system after you discretize, if you use the non-uniform grid, like you do the space discretization using non-uniform grid, or you so you could present it in a system that have something like in the structure is that including different components, like some fast component, some slow component. So this is, we call a multiple time scale system because it had a different time scale in each component. So in our work, we also focus on the case that where in many times that's the fast component is usually cheap to compute, but the slow component is very expensive. And so how do we design a method that can take basically a different time step for different component? Because with just a single or set time step size, then this would be very inefficient, it's unstable for the whole thing. So we want to use, for instance, if you have the slow path, you can use a bigger time step, capital H. If you have a fast component, you can use a small time step, like a little h. And then the question is how you determine the interaction, the time scale separation m between the two. I mean, you can think about other methods. They use a splitting method, like a strong splitting and IMAX scheme. But this is just written in low order, like a second order scheme. So we want to develop such kind of method, and there are some reason on that. We have some kind of the so-called multirate exponential method, and two different method depending on the right hand side. So this two paper on that. Okay, now I go back to so this kind of motivation, and then I'll go to the I guess that's just also some student attended the talk, so I designed this slide so that's can explain more about the idea. So again, now when you look at the classical method, what the problem now when solving such kind of system? So if you look just a scalar motor, just only lever, that you have the decay phenomenon problem like y prime equal to negative 100 y, so with a like a radioactive motor. And so you see that we can find the Joule solution clearly, let's say e to the negative 100t with the indice condition just 1. So it converts to 0 very quickly at t increase. Then when we apply the numerical method, we should expect the same behavior. Now, if you just apply the classical Euler method, explicit Euler method. Now, for those of you who would not, I mean, hopefully you know, but just on the right side, I have the box here with showing the idea of quickly to derive the Euler explicit and implicit Euler method. So you have the equation at the beginning, y prime equal fty. You integrate both sides from time tn to tn plus 1, and you just represent using the fundamental theorem calculus, and you can actually represent the Joule solution at tn plus 1 through the previous time step, tn, and then you have the integral. But for the integral, you can approximate, look like this picture. Here you have the area under the curve. Yeah? So you can easily see that this is the one way you can take the left hand side, take the left port Tn, then you build the rectangles like in red color I mentioned here, and then you have approximate the area under the curve by the area of this rectangle where you have the width it's just h because the length between t and 10 plus 1, and then the other side the height it's just the value of the function at tn y at tn, and then you immediately end up with the explicit Euler method. Okay, so this is a way to approximate this integral. This is the first order accurate. Now, similarly, if you use the right and port tn plus 1, then you can build this rectangle like in blue here. Now you create the so-called the implicit Euler method, because by implicit I mean that the yn plus 1, the unknown, is appearing in both sides of the equation. Here you have inside the nonlinear function, but here for explicit Euler, you only need to update from yn to yn plus 1, so you don't need to have anything to, so it's everything explicitly you can compute if you know the previous step. So if you apply this to this motor, you see that's the first one in the red is Euler method. You can represent the yn plus 1. You do a recursion, you can calculate it down to the n, and this is just 1 minus 108 to the power n plus 1. And therefore, if you need the numerical solution has the same property as the Joule solution, is that convert to 0, but it converts to 0 only if you take the base 1 minus 108 should be from 0 to 1, so that it converts to 0, which means that the step size 8 need to be smaller than 1 over 100. That is a restriction. Yeah, that's a time step restriction. Now, standard method like a backward or the implicit Euler, like the blue one here, we can do the same thing. We calculate, but we have now not yn but yn plus 1 to the term negative 100 here, and then but still you're lucky for this case because it's just a linear system now. So linear, so you can move here. You can show yn plus 1 like this, but this is now you have 1 over 1 plus 108 to the power n plus 1, it's all the way convert to 0 as long as 8 is positive. So it's all, so step size only positive is convert to 0 for without any condition on step size h. However, so now you go from the scalar to the PD model. Now you actually consider more general system. Like at the beginning I mentioned, is the first type is that when you digitize, you could have a very steep path on an inner path and a non-steep path on this path. So this is the first model that I consider is a so-called semi-linear problem. But the key even here is that the operator A has a really large norm or even unbounded operator like a Laplace. So then what we just saw in that example, simple example, is that we use the classical idea. We do this exactly this formula. We represent the true solution and using the fundamental theorem calculus, and we approximate this integral in bulk, which include all the difficulty like a steepness here. Like you see the Euler method or implicit Euler method you see. So in red, you see, for instance, like Euler. In blue, you see like implicit Euler. Then you can see that the classical methods, you don't need to do nonlinear solver. It's like a non-steep problem here. And you can, but you also see the step size restriction, like a 1 over 100 here. In general, you would have 1 over the ellipsis constant of the right-hand side, which in terms of PD, you can think of CFL condition, you can think like that. So you have the conditioner for the linear stability. And of course, you already need to do the function evaluation. However, this one is, you see, that's if ellipsis constant is really large or operator unbounded, then you have to basically very tiny time step for u or even not stable. And then you say that, oh, this is unrealistic for last case simulation. We cannot apply this. If you move to the most standard method, like the implicit scheme, you would see that, okay, we now have no time step restriction, but we have to show the nonlinear problem. We have to show the nonlinear, we have to use the nonlinear solver. Now think about this example. If you don't have just negative 100y here, but you have just like a y square, then you already have the nonlinear problem. You have to show the Newton method. You have to design the good predicational. But it also can introduce many times numerical damping and very sensitive, and in particular for the case that I mark a very good example for my latest book here is that for the highly oscillatory problem, like this scalar motor here, you have 100 at the frequency omega here, and you can see that the red one is like the explicit Euler scheme for form to plot the solution behavior. You have to use so many time steps. And the blue one, it doesn't perform better because it also have to use so many time steps. It's like the implicit Euler. What we want to design a method look like as a green curve, which is like a later we call advanced method. And this is exactly like exponential method can do for only 1, 2, 3, 4, 5 time step to reach the final solution instead of a lot like this. So this is so we want to do this kind of advanced method. Okay. So that introduced me to the second topic as the first let's say I say this is advanced exponential or multirate time integrators. So what is the idea of this so-called exponential method? Now same model here we have. Now here is the classical idea you have seen. Now the idea of exponential method is different. It that's when the problem has the semi-linear structure like this. Let for the moment it's just even forget about the nonlinearity T. You have just a linear system. Therefore, you can easily think, okay, I can represent as two solutions with using the exponential e to ta with the initial condition in the previous step. So in this case, we have this term un of tn plus 1 through the e to hat u of tn. Now, if you have nonlinearity there, you have just introduced the integral. Yeah? And then you have the kernel inside still the exponential. Well, this is look like you have the variations of constant formula you can use, or you can think formula with a term like integrating factor method in solving difference equation. Or in terms of Ph.D, we use the so-called Duhamel principle to represent that. Now, with the assumption is that G is non-steep, and so we can actually try to approximate this integral based on this, but we all keep the exponential time vector here compute exactly. So we end up with many different kind of exponential scheme, and this topic it belongs to the so-called exponential integrator, and this is a very good review paper by Osman from Numerical. Now, by doing this idea, I can see immediately the benefits here is that, of course, you don't have the you have the unconditional linear stability. You have method is immediately astable. You don't have the C upper condition when integrating the linear path of the PDE. So in the method you can see that you can also design explicit scheme. We don't like explicit scheme, so we have seen in the next slide. But then if you do that, then you can take much larger time set, and that's what we want to do. If you can take a much larger time set, then we actually can show very fast. So before doing this, I just briefly introduce the framework that we use to analyze the scheme we develop in terms of this exponential idea. To handle the steepness, of course, in this case, turned out to be the best framework using the semi-group framework. You can think about strongly continuous or analytic semi-framework on some Banach speed X. Now, there's two usual assumptions is that the linear operator A is a generator of an analytic and strongly continuous semi-group, E to TA on the Banach speed X. So this is requires some knowledge about the strongly continuous semi-group. Then with that, you can see that even the operator A could be unbounded, but you can actually prove that the exponential E to TA is uniformly bounded. So it's C constant. C is independent of the spectral side of A or of the norm A. Now, with the second assumption required that the solution, the regularity assumption requires solution use smooth enough with the derivative bounded in the Banach speed X, and then the nonlinearity is sufficiently open pressure derivative that you can take the derivative and along the exact solution, and they are all bounded because we need that for the analyze local error. But both of this one give you this like T is satisfied local ellipsis condition. So now how you design the first simple exponential scheme? The idea is just like I mentioned this formula before. So you represent using this formula. Now you keep the e to 8 UNTN, but you only try to think one way of approximated integral. So just take the simplistic way out. Just G is non-steep. You can think about, you can do the Taylor series expansion and only take the first term, G at Tn UN. Take only the first term. Then what do you get? If in that case, this become a constant vector. You can pull it out, and you have the integral of this path in the box like here. That I use the phi1 notation, phi1 HA notation to represent this metric function. Actually, you can compute explicitly, and it turned out that it's just e to 8a minus identity metric times the inverse of 8a. But I will not never do inverse here, but we just represent the scalar version notation. So if you integrate it, you can do that as well. Now, you keep that, you see that immediately that you can get this formula. It's that e to 8 AUN, and then you have 851 times G. Now, but this one you actually, sorry, the phi 1 is 1 over 8 of this integral. That's why you have H here. And you see that you end up with already exponential scheme, and we call this exponential Euler because the method is very similar to the way you derive the Euler scheme, but it just keep the exponential term here. Now, in the case that you let A go to 0, then exponential A go to the identity metric. Phi 1 also go to this, I think it's also go to 1. So then you get, as the identity metric, you get exactly the classical Euler method. But so that way the underlying method is an Euler method. It's an auto one. But you can also do a little better here because you see that if we need to compute this, we need to compute two metric functions, one term here, one term there, phi 1 and one term exponential. So we can do a little bit better by reformulate that using the equation of the problem. G is now f minus an, and then you can use this explicit computation of phi 1. You can reformulate that, and you end up with this just un here first, and then add phi 1, but multiply with the whole right-hand side vector, not only the nonlinearity. So add here. So this is exponential Euler method, and this is Hertz order 1. So this is so I just want to mention that how actually this one better to handle the stiffness. Now the Euler method take into account everything in F, but here introducing phi 1 of HA in front of that, so like the coefficient in front of F, which actually handles the stiffness of the system. So now you want to develop higher order methods. We can think about using the higher order quadrature rule to approximate this integral. Yeah? So you can think same way people derive Runge-Kutta method is that you introduce the intermediate stages. So you introduce something like here we need this is still unknown for E with Tn plus tau, so we approximate by some Un plus Tn plus CIH, which is still unknown, but we can again represent using this variation constant formula, and then we can approximate. Let's say you introduce the UNI approximate to that term, UN approximate eternal, and then you immediately end up with this kind of structure where you have the coefficient now no longer scalar like a Runge scheme, but AIJ and BI now they are the metric function of operator A, and then you can see that's in the specific case when A formally goes to 0, which is we don't have the steepness path, we have only non-steep path. Then everything go back to the classical Runge scheme. So you see that it go back to classic. By construction, you see the phi 1 there before, but by the construction, you will see that the coefficient AIJ and BI here, they are linear combination of this higher index phi function. For phi 1, you know that's when k equal to 1, but for other higher functions, by doing same idea, expand Taylor series for G, you can see immediately this metric function came out. So again, I can also reformulate the general scheme like I do reformulate for this exponential Euler by introducing the difference between the non-evaluated intermediate states and the current solution UN, which is I call DNI vector. And then I see that the first component is just like an exponential Euler, and then you have some perturbation based on vector DNI as coefficient IJBI here. And by doing this way, because of course we save one metric computation here, and it is also very convenient to analyze the local error later. So, so this is, and by the framework that I mentioned about the semi-group framework, we all see that on this kind of metric function can also uniformly bounded. So this is very important to the analyze of the steep order condition, because many people have been working on this, including in the past, for instance, even I mean Nick Truffren, John Butcher, but I think they only use the classical idea that just expand the coefficient, because when you look at the scheme, the unknown thing here is AIJ and BI. We have to find the order conditions such that we gain the level of accuracy. So there are some conditions posed on AIJ and BI, and that's a so-called order condition. But the way they do it is that if they expand it explicitly like this way, where you just think about the power theory of this, I think it's okay for non-stick problem where A has a norm is not too large. But if A has large norm is not very large, like I mentioned for steep problem, then this is, I think it's not feasible to do that, because then A to P, A to power, it becomes extremely large, and then you have time separations. So we came up with so exponential idea already have developed long times ago, but only until 2005, where Malik Osman analyzed and showed the method of order 4 with the steep order condition. So with this approach, before the EU expanding AIJ and BI, we would get a non-steep order condition. So non-steep condition means that our arrow bar at the end is still depending on the steepness, but steep order condition we would not depending on that. So they derive them in the Sinum paper method of order 4. And then I came up with Alexander, and then I worked and then derived the method of order 5. So you see that this picture here, this table here, that the order 4 would need 7 conditions like this in the reformulated form, and then we need 9 more conditions to get order 5. And you can imagine that all of this metric function the system to show. And by analyze, you would see that some term like a J here could be like a Jacobian. So in general form, you need to choose for any time step. So that's an arbitrary square metric J, or Z here is like 8A. But you also have to introduce, if you have high order method, you will have something like a K with the binary mapping, or the kind of complicated structure, but it looked complicated, but actually it turned out that we can show that we never expand explicitly like this. All of this process introduced this kind of metric function. So I will not show the tedious work to show that, but this metric function, size J8A, they are also bounded operator. Okay, so this size Ji also. So we came up with the condition so here, for instance, look what, for instance, this is a local arrow expansion, how it looks like for the method up to order 5, and with the new the notation for Cj and so on, then you can see that it's look like this, and so that means we never explicitly expand geometric function. We keep an object at a coefficient that is bounded operator. So that's the key thing. And so this is a remainder term is look like this. But now, in order to get the method of order we want, we need to zero them. So because this coefficient make the condition between for BI and then the condition for AIJ. So if you zeroing them, you get a steep order condition. So that's why, for instance, if you want to method order 3, you make psi 2a equal to 0. What is psi 2a? Psi 2a, the sum of bi, ci, minus 5j, so on, equal to 0 here. So you can show for the system of metric based on the phi function. Phi function is a known metric function. So then AIJ coming from the second relation here, and then then kind of we have a system to show, and then you end up with so now with my students 2 years ago, we get even method of order 6, but of course we cannot derive by hand at all because there are 36 conditions. But we can use the B-series approach, exponential B-series approach that allow us to make the connection between the algebraic order condition and with this graphing like a tree. We derive the let's say we want to divide order 6. We draw on the tree with a certain root that need to be satisfied on the tree with this order 6 nodes, and then we have to use different color, black and white, and so on. But we can do that, and then we immediately turn now to the order condition. We don't need to show by hand. But yeah, even look so complicated, people think it's complicated to show, but it's not at all. We know the way. When you know the way to show, you can easily to show this even system of metric function like this. So with that, we had the conversion up to order 6. And the arrow analysis based on the strongly continuous semigroup or another semigroup framework. So as long as you satisfy all of this order condition, you have the consistency, then you have the stability, because when you show for the global arrow representation, you see the convolution of the E to NJA, where this one is just also bounded quantity. Then you have the consistency, you have the stability, then you can actually solve the conversion as up to the method of order 6. So the difference between the numerical solution UN and the true solution is bounded by some constant and then proportion to the time step to about p from 2 to 6. But the important key idea here is that C is independent of the spectral side of the linear operator A. Okay. So then when you get the order condition, you want to show for the coefficient to get a scheme. And then here there are some practical scheme that I have. It's the first one is, I think the new method is like the fourth order 6 state method, which I call this a parallel stages method because there are two groups of intermediate stages can be computed at the same time because they are independent of each other. So it's like UN4, UN3, UN5, UN6, they are also independent. So you can compute 1 for UN2, 2 for UN3 and 4, 3 for UN3, 4 and 6, and finally the update UN plus 1. So this is like a for evaluation. You can already get a method of order 6. And they are all involve the linear combination of 5 functions. Phi 1 time vector, Phi 2 time vector, so on. So there are linear combination of 5 functions. And they say the same, see there's a scaling inside. So the difference is that the previous scheme, like the one Mallet-Hopper-Ostman derived fourth order, they have different linear combination in one intermediate stage, and they require 6 evaluation to get it. Here's 4 evaluation. But here is also satisfied the steep order condition. The setup here, they sometimes when they show this, they have to relax order condition, but we actually can show in the strong form as well. So for the method of order 5, I have also another version. It's like an even stages, but behave just like a 5-stage scheme. It looked like this. I just explicitly show the whole thing, but it just you can see that's just an inner combined of 5 function vector. And later we have to discuss quickly how we compute this, but this is can be done. Now this is just an experiment to show the efficient. There's a new scheme. So the fourth order, the fifth order that I just showed, compared with the previous fourth order that in blue here, that the one that in the paper, Sinum paper by Hopper-Osterman. And the one in green is that the paper me with Alexander Osterman in the fifth order and with the 8 stages, which is the previous version. But we tested in a nonlinear 1D Schrodinger equation here, and we use the spectrum methods as a space equalization, and so you can see the matrix A just become like a diagonal matrix like that. Then you have a nonlinearity like this, inverse Fourier transform of this. And then you see that, okay, we are more, so let's say, look at the fourth order, then the pink color, the new method is much more accurate than the blue one with the same set of step size that you use. And then also the fifth order also more accurate than the before, but we also faster. You see, look at the same accuracy, similar accuracy, 10 to the minus 4, 10 to the minus 6, so on. We are spending less time than getting that accuracy. So you see the curve on the left side of this blue and green. So that's the thing. And then now we also can do adaptivity on time stepping as well. But I will skip that part. It's just you can do a standard way. You can also do that. Then you test with 2D advection diffusion direction equation. You can also see that they are doing better than ODE15S in MATLAB, because here you see the accuracy is also much more, and then we are also faster. And then the last picture to show the steps taken to get the same accuracy at the final time step, at the final time. So the blue one, it's the new method. It's clearly can take much larger time step size than the step size chosen by ODE15S with the same level of accuracy. Okay. So now we focus on the second form with that. So what about if we have the full nonlinear problem? So so in this case, you can think about the idea of linearized system, dynamically linearize every step, and is presented the so-called So if we don't have the semi-linear structure, we linearize that, we get a Jacobian here of the whole system time J n time U, and then we have everything else like the nonlinear remainder term, where you have just original linear f U minus J and U. So then you have a semi-linear structure again, but the point is that every step you have to update the Jacobian and also nonlinearity. But the advantage you gain here is that you have the nice property is that the Jacobian of the new nonlinearity n here is vanishing every step. We can simplify the organism significantly. You don't need such a lot of organisms like before. And then also have moving everything with a steepness to from capital F to the linear path here. And then when you have that, you just apply the exponential arcade scheme that I introduced previous part, and then you replace A by Jn, replace G by Nn. Then you have the schemes look quite similar, but the metric function have to compute that as a Jacobian. But the nice thing is vector DNI no longer oblique of h, but oblique of h squared step side. Okay, and you have a second order method for free. If you look at the green term here, and people call this is exponential Rosenbach-Euler scheme. And then similarly, we can actually prove up to mass convergence method up to order 6. And then now instead of using 36 order conditions, we only need, I think, 7 conditions to get order 6. So this is much less than before because of these nice properties. Here says that something had to analyze with the proof conversion proof because the Jacobian changing every step, but it can be handled. So I will not go into detail, but now the thing it can show much because the organism much less, and then we spend much less number of stages to derive the scheme as well. So we have some even version like we call a super convergence scheme because this is like a 2-state explicit and 4th-order scheme like a exponential Rosenbach for 2. 3-state 5th order. Then we also can have the parallel stages where for instance, you look at this scheme PXP RB for 3, where we have UN2 and UN3, they are just independent of each other. We can compute by in parallel or just compute simultaneously at the same one evaluation to get both, and then you have the second one. So it's just 2 evaluations to get a scheme to implement the scheme. Okay. So I will just show some application related to this scheme also, but recently we just also derive a new class of exponential method. The work has been submitted, but now we look at the also same model types that I say that's a semi-linear structure, but we further work on the variation constant formula. We further expand that, and then we end up with a structure look like you have you can further expand the n here. Then you have the basically not like exponential Euler, but you also have introducing additional term s squared phi 2 with the n prime f. And you can reformulate as f prime f because this is the second derivative in time. So you have this thing and add with the integral now with the hq term here, and then not like AP4. Then you can think about the way to approximate this. You would introduce a new exponential scheme, and this is the so-called 2-derivative exponential method we call. Or you can think about, I can call also exponential Hermite integrator because we use information of a derivative as well. But to just briefly introduce that this is can be done. That's now you see the term, an additional term here, and then s squared in terms of the sum. And then the DNI is no longer like before, but there's 8ni involving the derivative of nonlinearity. Okay, so but the metric function is still fixed as of the linear operators, so no Jacobian there. But this one is now, you see that still inherits the same property of exponential RK, but it can get much higher order and then less number of stages because of the way we have involved s squared and the second derivative information. So you can also analyze, but the nice thing is that instead of spending also a lot of order conditions with exponential RK to get order 4, you get 16 order conditions. But now we only need 4 conditions to get orders 4, and then this is also using the fixed Jacobian, not with the full Jacobian like a Rosenbach idea. And here is also we can get, you see that's a two-state Fowler version in this version now involving like this form. It look not the same exponential Rosenbach. It's different because here you have phi 2 for a term, and then everything is of a fixed Jacobian, of a fixed linear operator L, not a full Jacobian. But you have the vector now changing, involving the second derivative information. But this turned out to be even more efficient than the Rosenbach scheme. You see that this picture testing again on 2D advection diffusion reaction problem. Okay, and so let me briefly mention about, because you have seen many scheme like exponential scheme like that, it just require actually every state you compute and in a combination of 5 functions. So there are several efficient codes that are available in the literature. For instance, Nick Hamm's code in Xenom 2001, linear interpolation in Marco Keller in 2016, adaptive Krylov, Nielsen and Wright. And we improved one of the code to make it faster using the incomplete orthogonalization method in this paper here. So they all just compute. This code allows us to compute even multi-linear combination at the same time. As long as the same set of vector, but even when we allow to different scaling inside the magic function, so like a row 1, row 2, and row R here, we can compute by one evaluation. So the code available on GitHub you can download. So this is simultaneously compute the linear combination of magic function. Okay, so this is I briefly mentioned at the beginning, but anyways, that's the idea when with the multirate time integrator is that you design the method that can take different time steps for different components. And luckily, with the exponential idea, we can even also turn out that to get a scheme of multirate exponential scheme. These are all the previous work that people have done. That they presented in a different name of the scheme, like a partition additive numerical scheme or extrapolation lower method, or the multirate GAT scheme. But they all require the full set of coupling, decoupling organisms. That's require a lot. And then this is not easy to get my set of order 5. I think so far they get up to order 4. And then difficult, so this is it typically is resulted in a huge number of conditions, and it's not easy to show at all. And then we want to develop the exponential multirate methods that can overcome this. And then the idea is that I look at the idea of the backward arrow analysis that instead of doing so look at the difference equation that take the numerical solution as a true solution, but and then try to build a modified fast equation that so for instance you have the fast and slow component. So the idea is that integrating the fast time scale exact solution through the way you find the g of tau, where the linear polynomial to approximate to this epsilon, and then taking the exchange information between the two. And then when you look at the exponential scheme, then you can actually see that the linear combination, also the solution of some linear combination of 5 functions, it's a solution of some modified ODE that you can design. So I just mentioned that we can find such kind of G tau in terms of this idea, and then using exponential scheme without we can inherit the order condition from exponential scheme, and we can put in structure form exactly what they are looking for, like a multi-rate infinition methods. Okay, so this is beyond this scheme. So I just mentioned that. So. And then we also can consider the case that the operator also full nonlinear operator also. And we design the so-called multirate exponential Rosenbach as well. So we have basically the key idea is that we look at the coefficient of exponential scheme, and then you actually formulate at the solution of some linear ODE, where you have to build this kind of rate polynomial. Okay, I'll skip this part. We have this scheme, and then we have tested. We prove the conversion. We compare with the previous methods in terms of number of OD we use, and in terms of the efficiency. But okay, I'll due to the time, I think I have to talk last part about the application. So you will see how exponential method can be applied to applications. So the first application in visual computing is based on these two papers. How do we do the real-time simulation of this electrodynamic system? So you can think about like people doing simulation in computer graphics. They do a lot of things with the structure, deformable moving objects, and so like a cloth fiber, textile, flexible solids, and of course, the model coming from even finite element methods to get a model, or you can think simple like this way I put here, that think about the Newton's second law of motion that describe so you have the mass time acceleration equal to all the forces acting on the system involving the spring, damping, external forces. Then you end up with a large system here, like you have mass metric m, the acceleration second derivative, you have the k metric spring, damping, external forces with the initial position and velocity. Then this is a large number of particles. It's a 3D system, and then spring metric is usually very steep. So this is challenging for the classical method. So this is so we use the exponential scheme to compare with them, and then we are doing much faster but the same quality of simulation. So for instance, here the classical method they use, for instance, let's say they just use Numerical fourth order method, which is explicit scheme and then has the limitation in terms of stability and very slow. As I explained at the beginning, is the motivation path where you explicit Numerical scheme, you would have a very time step restriction, and so they use standard method. It's also expensive and introduce numerical dissipation and so on. And then they use a very new method, a Gaussian time integrators that like allowed to do with the stiffness, but still very sensitive to the stiffness. So we want the method that can actually handle with the error constant is independent or much less sensitive to the stiffness, and so that we can take larger time step where therefore we can speed up the computation time. Then we did a little bit more thing here that instead of doing the standard way to reformulate a second order system in terms of the first order by introducing the vector position and velocity, but we now introducing in their application the metric is usually positive semi-definite, and it's the square root exists, so we introduce this square root time position and velocity, and it end up with a system where the coefficient metric is now skew symmetric instead of non-symmetric like that. And so we gain some advantages in terms of the exponential of this skew metric. It just has a norm 1, and it's symplectic. And so the simulation have been done in several models, that testing model in that field. It's like a deformable object, nonlinear textile, co-rotation reformulations, and complex steep system and couple system. And so before showing this simulation, I can see that I can show that this is basically you see that it's consistent with the theory that here if you increase the steepness even for group bonding system, that we have extremely steep system where you have 10 to minus 6, 10 to 6, 10 to 8, and 10 to 10. So green, yellow, red color. But you see that on the classical method, even Gaussian time integrators, second order scheme, that they see that the arrow is significantly increasing when you increase the steepness. But you see this curve here, there's three curves lie on each other because they are not independent of the steepness, much less sensitive to steepness. So you see that even increase steepness, you see there's the same quality of arrow. And then they also preserve the energy up to the certain like time scale. Okay, so this is the nice thing. So you can look at this view simulation also. Yeah, on also, sorry, this is I have a new web page already, so you can also look at the new web page, so that on this simulation, that it's very cool to see that. I would say that for the classical methods, they can also do that, but we are doing much faster. That's the key message, is that same quality of simulation. Instead of spending a long time, we can shorten by a lot. So you can see the speed up in the next slide. So yeah, this is like some kind of very cool simulation that they do in this field. And then I was surprised that I did with a small system first, and then they tested on this kind of motor. So so this is I'll just, you can look at this. Also, this is a video introduce our work from the C-Graph trailer. So, but I would just, you can look at the web page. So due to the time, I
This video highlights
I just skip to the
a new
part that,
multi-species model can simulate the interaction between water and porous sand as this dam
I
is.
think it's 36
This
seconds.
new extended finite element method robustly handles cutting this rubber plate with an arbitrary and complex cutting path. A new integration method accelerates accurate simulation of stiff systems like the motion of these fine strands of hair.
Okay, so then you see the speed up, you see significantly here. So we span only for the hair simulation, very complicated system, 6.48 million particles. We have just 44 minutes instead of they spend 31 hours or 80 hours, so almost 3 days, more than 3 days. So this is showing the benefit of using this exponential scheme. So we gain the speed up factor much, ranging a lot, a lot compared to the classical method. Same thing for the test crash test for the car simulation. Also in this we spend less than a minute, and then they spend an hour, or the best method is 9 minutes, and so on. So yeah, this another application in numerical weather prediction I did with some collaborator from Canada before, is that we can use this exponential scheme to design also faster and more efficient method to on the solid water equation on sphere. So sorry, Julia, how many minutes I have, or it's already past the time? Sorry.
You can continue. Don't worry. Just continue.
Okay. So I'll just speed up this. Okay, so this is done.
Yeah.
So I just want to say that this kind of methods can apply to this system as well, the solid water equation on sphere, and we can actually doing faster than the semi-implicit semi-Lagrange that I mentioned, the popular scheme. And we compare with the people have used exponential scheme before, but this is a non-steeply accurate method. We compare with that, and then this directly compare with other scheme, indirectly compare with other scheme. So here's the motor look like this, and for the space dedicatization, here we use the file and volume method, and then the grid style look like this picture here. And then you have a large system at the end. So we use two new exponential Rosebud scheme compared with this one, and then we see that so they own kind of showing the expected conversion rate, and then they are faster than. So the black one is the one that they used before the classical exponential scheme, but not specify the steep power condition. So we can take much later time step here, and then we can see the speed up from 2 to 3. The speed up to 3 times faster. Okay, so this is the same thing, the same simulation. Even with if you compare with here, AK4 takes 30 seconds, semi-implicit around 15 minutes, API 2 hours. We can take 3 hours, get the same quality, same simulation. So like a time step, we can take much larger. Okay, so this is the last application I showed today. That's with some joint work with my student and Julius when he visited Mississippi State before. So we look at the system in genetic regular system where you can see the gene expression and modeling by this kind of deterministic model. And in that work, we developed a second order derivative exponential scheme that I mentioned idea in the talk. But we can apply, I did the starting point of this scheme that we get a more general scheme later, but this is a second order scheme. And so we actually also see the same thing, that we can test it with all the model they tested in those paper. and we select a 3-chain system here. Then you see that the new scheme is much faster. On the left here, we see much more accurate and compared to the other method they use, like the green integrating factor scheme or rule second order scheme. So we are much faster with the same level of accuracy. And also this is a complicated model that has I think 13 equations and a lot of more than 50 parameters, and so yeah, my student has to spend like a month to get the Jacobian metric of this, but anyway, it's done, and then we actually see the same thing, that we can do much more efficient than the method they used before. The battling cell cycle model. Okay, let me conclude the talk. It's like so we develop the new and fast and accurate exponential method and multirate time integration scheme for Ph.D. And multiple time scale model. So we have 3 applications I just showed. And then for the future, we are currently working on building also the kind of new methods for the way to implement not only the first order problem, but also second order in time exponential integrators. And we also want to develop the method that can preserve the structure of the problem. And we also develop other kind of scheme that combines the techniques and hybrid scheme and adaptive and incorporate in other application areas. With that, thanks you for your attention.
Yeah. Thank you so much, Luan, for your very wonderful talk. I know there was not much time. I knew you could have been able to speak more, because I know you are a great teacher. I know. I know.
Sorry, I just also over time. I just I'll just talk about some.
So can we if you have questions, can you just raise up your hands, and let's just maybe we'll take some few questions, maybe two questions or 3 questions, because we are spending a lot of time.
I see one of the question in the chat, like, can I get the programming language of the code? Yes, you had mentioned the code that in the GitHub link that I introduced in the talk. You can download that to implement the exponential scheme. So like so this is I think this is in JCP paper in 2019. That's a code that you can download. It's still, I think as a number of people have used this. So this is this one here. You see the GitHub link here. So you can go to my webpage also. You can see that link to the code. Yes. Okay.
Okay. So any other question? If you have any question, any question from the participant? Anybody has question? Oh, no questions. Oh, okay.
Hello.
Yes, okay, yes. Can you
sorry, I have question, but my questions are not directly on what the professor.
What's your name, please? What's your name?
My name is Adamu.
Okay.
I'm a Ph.D. student here in Kimongot University of Science and Technology in Thailand.
Okay.
Yeah, I'm working on mathematical modeling. Because the prof talk on the temperature, humidity. So I am working on vector boundaries, where I want to look at the effect of temperature, humidity, and rainfall within my system. So actually, that is what motivated me to join this session. So, and I've never seen something similar to it throughout the discussion.
I'm sorry, can you repeat the question? You want to ask about
what I'm saying, I'm working on vector boundaries. So actually, we have, I want to incorporate climatic variable, that is temperature, humidity, and rainfall into my model equations. So actually, I joined this session for me to see how can I navigate to use those climatic variable into my model equations.
So if
Well,
you have the motor, when you have the motor, as I mentioned, you after discretization, you usually end up with this system. For instance, like this motor, you would can, as long as you can put in this kind of framework, we would have a different exponential scheme to for the, I mean, I'm talking for the time integration part.
Okay.
So as long as you have the motor, if you want to show numerically, I believe you have to do space digitization also, either finite. Many people using also finite element method.
Okay.
But as long as say when you do that, then you would come up with a general system like this. So I say this would look like ODE but a large size. But then we see that in the talk you have either, I'll go back to that slide. Either you could have a full nonlinear model or you could have a semi-linear structure, and for that we have a different version of exponential scheme that can handle the
yeah.
situation. For instance, like so here this one is, I say here this slide. You see, you have a motor here. This is like I don't know whether the model fit with that, but as long as you have this, and then you look at the structure of the right hand side, either semi-linear structure or even full nonlinear like this, then we have a different exponential scheme to handle this. And in our new network, we even allow to have a steepness on the nonlinearity as well. So steepness can come in from both paths, linear and nonlinear path. So and also we have, I haven't talked about this work here, but we have not only the first orders in time system, we have also the work on the so-called exponential nitrom scheme. If you heard about the nitrom Runge scheme, then this is for the second order in time problem, like the wave equation. But here I haven't talked about that, but we also have the
Yeah.
new exponential scheme for the second order in time also.
Yeah. Yes, thank you. Any other question?
Thank you, Prof. Thank you.
Thank you. Yeah.
Any other question? Okay. If there's no question, then okay, maybe I ask a question, maybe to further help people. Luan,
Yes.
how can we approximate in the two derivative method the numerical solution, that's the exact solution now? If you go to U of T.
Two derivative, yes. So this yeah, see it
Where
here.
you have the double integral, yes. So how can we estimate this double integral?
Oh, this is here. Maybe I can open so you see the quadrature root to do this. Maybe this form is maybe hard to see, but if you look at the quadrature root to approximate this integral, you would keep this part here. You only need to approximate something related to the nonlinearity, which is this is like a this is like the third derivative of n prime u prime. So like this is related to the second derivative of the solution. Then you end up with a quadrature root involving some you know, that the coefficient AIJ, which is still the linear combination of those five functions, and then you have 8 and 9. Now it's like this form. You see that is like a big up h.
Okay. Okay.
I mean, I can show, but this is in our paper. We explain more detail on this part. Yeah.
Yeah. Because so what my question is really saying is how to approximate that. What you have under the integral. You know, for if we have f, you know, we can use what they call it. We can use either Newton divided difference. We can use Newton Gregory. You know, but for this one that you have the n prime of something, how do we approximate that function?
Oh, this one is we compute like this is like you only need to, so this version I there's some equivalent version, but this version you look at this term n from f, so this is the Jacobian of the non-integer only here.
Okay.
So not the full Jacobian, but if for some example you can compute exactly like a advection diffusion direction system, you can do that, but If not by chance, you cannot really we have to approximate this Jacobian, then it would be resulted in the so-called two derivative multi-step exponential scheme. Yeah.
Yeah, multi-step. Yeah. Okay. Thank you. So any other question? Again?
Yes,
Okay.
there's
No,
a question.
Okay, please, can you ask a question?
Hello, are you hearing me?
Yes, we can hear you.
Yes.
Okay. I look at the work. I can't see you only work on OD. Your scheme is on OD. I can't. You may you said partial differential equation, but your work is just on OD. And
Yeah.
you said couple system. I cannot see that it's a couple the same of
Oh,
differential.
you mean that the some model that I consider in my work is that of course we publish the code only for computing metric function in exponential method, but you mean like the couple system like this?
When we say couple system, no, it means the variables are interwoven with the system of equations. So,
That's what
yeah,
is showing you on the screen.
okay.
You can see that one is showing now where the pointer is coupled. You can see it's coupled.
Yeah, this couple system, but in the paper we public of course we have the code to implement. But what do you mean by like of course we do not publish the code for specific example like this. But this is clearly you can still put everything in the form of this motor, and then you can apply the code. Yeah.
Yeah.
Okay.
So you
And
have to
again,
do some work before you apply. Like you have. So you see, this is what I talk here. It's like you have a number of equations in the system. You can put in the form of the whole thing like a vector form, and then you can introduce everything. You have the even so. Let's say this model you have the couple system, two equation. You can introduce u and v in a vector, and then you have a capital U with a new unknown, and then you can put everything in form of the new system of the first order. So you still can work on that. Yeah.
okay.
Okay.
And
Thank you.
so also your mass spring dam system that you pointed out is a second order
Yeah,
OD.
second order in time.
And what you have is your
Yeah,
scheme.
here.
You use it for first order. And what can you say
So
about that?
so the second order in time you can reformulate as the first order in time here also.
Yes. Then we get
you get
a system of two equations. Agree?
Yeah. Sorry.
Then will it work with a system of two equations? What you have done, or you need the extension?
What do you mean by like you talk about the second order in time?
You illustrate for us using first order OD. But when you mention first order, are you getting it?
First order?
Yes. When you are writing your this integrator or something like that, you derive it from u prime of t equal to what? F of a t comma u of t. Then you splitted it into au of t plus g of t comma u of t.
Yes.
And this is first order OD. Is that not so?
Yeah.
Yes. Sorry, so you can see the screen. Look at the screen. You can see that you reformulated this second order as the first order system. Can you see that? Can you see the screen now? You can see X prime.
No, something wrong with my system here. I can't see. So sorry. Okay.
Sorry. Okay, that's right.
Okay.
That's right. Sorry. Okay.
So thank you.
Oh, you cannot see the screen?
Yeah, something wrong. It went off here. My screen something became blank. I can only communicate. Sorry.
So,
yeah, but My point is that even you have the high second order in time system, you can reformulate as a first order, and then you can apply. And then in our new work, we haven't public yes, but we can also work on the second order in time system directly without like introducing, without reformulating as a first order. We still have the exponential nitrom scheme for that. Yeah.
Okay. Thank you, sir.
Okay. At this stage, we want to say a very big thank you to Professor Luan for your very interesting talk. And I must thank you very much for your assistance and support in my career. And, you know, we've known ourselves since 2012, you know.
Yeah, thank you so much.
All along, you have helped me, you know, to create opportunities for me to visit the US twice. Okay, so at this stage, I want to say thank you, and I hope you would like to share your slides with us so that we can share to the participants after.
Okay, yeah.
Okay, thank you so much. Okay.
Yeah, I can send you by email. Yeah.
Thank you very much.
Yeah, thank you. Yeah.
So bye-bye, guys. Bye-bye, everybody.
Yeah, thank you, everyone. Yeah.
Thank you very much. Bye.